Hi everybody. In this video we are going to introduce governing conservation equations for three variables that we care about the most within the fluid. Specifically, we're going to take our generic quantity x and replace it with velocity representing momentum, concentration, and temperature representing heat. So we're going to have three new equations, but each of these equations is going to be based on the same principle, essentially that the rate of change of that quantity in time is going to be determined by how the fluxes around that point vary spatially. We also saw later on how we can actually define this flux based on molecular diffusion processes. However, what we're going to add now is definition of other terms that are independent of the fluxes we introduced before. Another difference is that now we are going to consider instantaneous values that can vary across time rather than starting from the time averaged quantity like uppercase U or capital X and capital F, because these mean quantities exclude fluctuations, which based on the previous video, we know to be important to the mixing process. Later on, we're going to apply time averaging again in order to reveal the role of those fluctuations in mixing. In terms of notation, there are two ways that I'll be indicating time averages. So uppercase lettering for variables will indicate a time average, and a bar over a lowercase variable will also indicate a time average. We are going to start with the conservation of momentum. If you consider momentum per unit mass, it is equivalent to the velocity. And specifically, we'll be considering the horizontal velocity u in the horizontal direction x, so how it's varying along x, rather than looking at how it's varying along depth z. And the reason for looking at x instead of z is how we can relate the momentum flux to the shear stress using Newton's law. So the vertical flux of momentum between 0 and 1 and 1 to 2 can be directly related to the shear stress that is resisting the flow along the x direction. So we are going to consider the governing equation that conserves momentum in terms of forces and accelerations along that same x direction. In addition to the flux contribution, you also have an internal source of momentum, which comes from the pressure, and specifically how the pressure varies across the flow. So if you have a high pressure region on the left and a low pressure region on the right, this higher pressure on the left is going to help push and accelerate the flow towards the right and lead to a positive increase in the momentum. And likewise, you can get the opposite effect if the pressure out is larger. The way to represent this pressure contribution mathematically is to take the negative of the pressure gradient along the x direction. If you take this definition for the vertical flux of momentum and plug it into this middle term here, you get a cancellation of the two negative terms, and you end up with a positive contribution that includes two derivatives. So this conservation of momentum in the x direction results in what is known as the Navier-Stokes equation for the velocity component u. And it includes a rate of change component, which is essentially how the flow is going to accelerate, and then a contribution from the pressure gradient, which is an internal source of momentum, and then the net effect of molecular diffusion and its flux. Moving on from the momentum, we are now considering the concentration, and specifically we are looking at how the concentration varies along the direction z, so things are a little bit more straightforward. We can employ Fick's first law of diffusion that defines the flux that you get from molecular diffusion. And we can also employ the same basic principle of how that flux is related to the rate of change. What we need to add in addition here is an internal generation or loss term. So there may be some mechanism within the fluid that allows concentration to be directly increased or decreased at that point in a manner that is independent from the fluxes. We'll represent this direct generation or loss using just its own variable s, and you get a very similar equation from what you got with the momentum after you plug in Fick's first law of diffusion into this center equation here. So what you end up with as a result is known as Fick's second law of diffusion. This is defining the rate of change in concentration and how it is directly related to gains and losses at that point, and also the net effect of molecular diffusion again. This internal direct gain loss can come from a variety of processes. Mostly they are going to be related to chemistry and or biology. So you might have some sort of an organism that is consuming carbon dioxide and outputting oxygen, for instance, or vice versa. So the concentrations of those elements are going to vary due to that biological process that needs to be represented in your governing equation. Finally, we have the conservation of temperature, and I'm giving this variable a subscript W to differentiate it from time. And we are going to consider how temperature varies along the direction Z. We have Fourier's law of conduction to define the flux in terms of the molecular diffusion. We also have the basic principle relating that flux to the rate of change. And in this case, the additional sources or losses are going to be direct gain or loss from heat. So H net here is some sort of a net heat exchange. And you can represent this in the governing equation using a ratio of that net heat exchange with a couple of constant parameters, the fluid density and the specific heat of that material, which defines the capacity of that material to convert heat into temperature change. And then, as before, you have a similar representation for your molecular diffusion term. So the resulting equation that you get for the temperature is known as Fourier's heat equation. It has the rate of change, the direct gain or loss of heat, and a representation of the molecular thermal diffusion. We can replace this net heat exchange with a solar irradiance contribution that happens below the surface of lakes. And this comes from previous lecture material on thermal stratification. So this gives us a more direct connection with what we talked about previously within the unit. And one thing that I will note is that when we talked about this temperature change previously, it neglected the impact of diffusion due to the fact that diffusion tends to be much smaller than this direct gain or loss. So the resulting conservation equations that we get at the end of this exercise are three equations that look very, very similar to each other. We have a net rate of change on the left, some sort of an internal source or sink of that quantity, and then a net effect of molecular diffusion. And the equations are given in terms of the Navier-Stokes, Fick's law of diffusion, and Fourier's heat law. What we haven't done to this point is to specifically define what this rate of change is, and in particular, what this large d represents in the derivative. And so that is what we are going to move on to next.